Hello guys, in today's video we are going to discuss Pyridinium chlorochromate. It's also abbreviated as PCC and also known as Corey-Sachs reagent. You can look at the structure right here. The structure has a pyridinium ring and with it we have a chlorochromate group attached. It is commercially available and interestingly it was discovered by accident. The reagent was originally prepared via the addition of pyridine, which is this compound, the nitrogenous ring, into a cold solution of chromium trioxide in concentrated hydrochloric acid. Now, let's look at the use. PCC is used as an oxidant. In particular, it has proven to be highly effective in oxidizing primary and secondary alcohols to aldehydes and ketones respectively. So it's an oxidizing agent. The reagent is more selective than the related Jones reagent because, as we can remember, in the Jones reagent, the carboxylic acid is produced due to over-oxidation of the aldehyde. Here there is little chance of over-oxidation to form carboxylic acid as long as water is not present in the reaction mixture. A typical PCC oxidation involves addition of an alcohol to a suspension of PCC in dichloromethane. So in the reaction we take the alcohol and add it to a suspension of PCC, which is the pyridinium chlorochromate, and we have dichloromethane also present in the medium. Now let's look at a reaction. Here you can see we have taken this very complex molecule and converted into another complex molecule with the help of PCC. Now let's just look at what has changed. The groups in the starting are the same. All of this stuff remains the same. As you can see, there is no change in the stereochemistry or anything else in the upper half of the structure, while in the lower half there was a alcohol right here and it has been converted to a ketone. So you can see it's a very selective reaction and it does not affect anything else in the reaction. This structure right here is triterpene lupiol and it has been oxidized to lupinone, and these are used in pharmaceutical and cosmetic industries, so you can look them up to know more about them. Now let's look at the general reaction. We take 2 moles of PCC with 3 moles of a secondary alcohol, and we get all these byproducts and we get the ketone. Because a 2-degree alcohol cannot be converted to an aldehyde, it will be converted to a ketone. If it had been a 1-degree alcohol, we would have ended up with an aldehyde right here. Now let's look at another important point. The biggest disadvantage of PCC is its toxicity. All chromium 6 compounds have reagents have this as a drawback. We saw this in Jones reagent as well. As I have written it, it is shared with other hexavalent chromium compounds. Other more convenient or less toxic reagents for oxidizing alcohols include dimethyl sulfoxide, which is used in Swern-Fitzer-Moffat oxidation, and hypervalent iodine compounds such as desmartin periodinane. Another thing to note is if we had a tertiary alcohol in the starting, the chromate ester formed from PCC can isomerize via 3,3 sigma tropic reaction, the Babler oxidation. I'm not going into the details of this reaction too much. I'm just making a point as to what happens when we take a tertiary alcohol as the starting substrate. Other common oxidants usually lead to dehydration because such alcohols cannot be oxidized directly. PCC also converts suitable unsaturated alcohols and aldehydes to cyclohexanones. This pathway, an oxidative cationic cyclization, is illustrated by the conversion of citronellol to pulegon. PCC also affects allylic oxidation, for example in conversion of dihydrofurans to furanones. You can look up these compounds to know more about them. I'm not going into excess detail. I just wanted to bring that out so you know what happens with a tertiary alcohol and what is the oxidative cationic cyclization. Thank you.